So again, thanks for joining us for today's Wednesday webinar presentation. The topic today is a tour of the stress analysis tools that are available for SOLIDWORKS. So SOLIDWORKS is a 3D CAD system. Its bread and butter is designing parts and components and assemblies in 3D. Over the nearly 20 years now since SOLIDWORKS' inception, developed a range of auxiliary solutions, of complementary solutions to do different things, whether that's in electrical design, whether it's data management tools. But the focus of today is to start to talk about some of our simulation capability, our analysis capability. And the reason why we're going to, well, the companies use digital analysis, it's pretty well understood here in 2015, but it's a way to make earlier predictions of the performance of components and assemblies and products earlier in the design process. Right? Typically, go back 20 years, you're in a state where to predict whether something is going to work, you have to work right through a detailed product design, build a prototype, and put it on a test rig in order to, or send it out in the field as a test unit to see if it's going to do the job. Because that's still a part of our process, but if we can run a number of iterations prior to that physical prototype, we can get so much further into the design process. And that's really what we're looking to do in SOLIDWORKS. And one of the big focuses of all the auxiliary tools that SOLIDWORKS looks at to bring on board is can they streamline that design process. There's a couple of things that are unique about doing analysis inside of SOLIDWORKS. The first is that it is designed to be easy to use and to fit into a designer's workflow. It's integrated, well, it's in SOLIDWORKS, so it uses familiar commands and work processes, so a shorter learning curve. But in the background is a very, very comprehensive and well-regarded analysis solver engine. That has 20+ years of market experience behind it. It's completely integrated into SOLIDWORKS, and the best thing that's going to give to you is when you run an analysis, you're not exporting your SOLIDWORKS file to another program. Right? You're working on your active model, so you can make adjustments, and those changes are ready to be analyzed instantly. And lastly, here at Hockridge Systems, we're a single source solution for everything related to SOLIDWORKS and some things that aren't in SOLIDWORKS as well. We have a dedicated analysis team that lives and breathes this stuff day in, day out. And so if you need training, you need support, we're a one-stop shop for you to contact. So when we talk about analysis in SOLIDWORKS, we really break the world down into three main areas. There's 5 listed here. Motion and sustainability are kind of niche applications, but we talk about stress analysis tools based on an FEA methodology. We talk about flow analysis tools, flow and thermal analysis tools based on CFD approaches. And we talk about plastic injection molding prediction. And today we're going to talk exclusively about the FEA packages and kind of take you on a tour from the simplest to the most complex tools that are available. Again, when we're looking at simulation, we're trying to determine the product quality and how it's going to perform in real life. And while there's some variation, the primary aim of FEA is looking at strength, right? Is it strong enough to withstand this loading? That loading might be static, it might be dynamic, it might be highly nonlinear, but that's our fundamental question. Is it strong enough? Most of the time. Once we prove that it's strong enough, second question becomes, can I make it less expensive? Right? Can I remove material and still maintain its strength? Can I eliminate unnecessary strengthening components? Can I do that? Those are generally the two questions we're asking when we look at stress analysis. Now, within those two questions, you can see a whole spectrum of different types of analysis, different analysis strategies, different ways we can apply loading, and we can really break it down into these three SOLIDWORKS simulation packages. And so there's a lot of bullets on this slide. So let's take you through them kind of item by item. And we will start with something that is in every single license of SOLIDWORKS. It's called SOLIDWORKS SimulationXpress. Okay, you'll find it in the Tools menu of SOLIDWORKS, Tools, SimulationXpress, and it's in every single license. Everyone has access to this. It's intended to be kind of a sampling of the FEA capabilities from some of the later packages. It uses the same analysis engine, the same solver as our full-blown stress analysis tools, but it has some limitations. It allows you to analyze one part at a time. That's it. No assemblies, no multi-body parts. It has limited inputs and control, fixed restraints only, forces and pressures only. It cannot adjust the mesh in certain areas. It can only adjust the global mesh density. But it does feature an optimization tool. We can adjust one model parameter to improve the model, to make it better, to make it lighter while meeting a certain strength goal. And you get some pretty solid result information. It's more of an overview. You're not going to get the depth of interrogation you get from the full package. But we can share those results to eDrawings format, which means basically anyone with a web browser or the eDrawings downloaded software can view these stress results in 3D, which is pretty neat. One new thing you might notice as you install SOLIDWORKS 2015 is that we're asking for registration the first time you use SimulationXpress. It'll direct you to a link to mysolidworks.com. You'll log in, and it'll give you a little registration code. What we're trying to understand with that is who's using, what does our community of SimulationXpress users look like, and what can we do to cater to them? We don't have a lot of that information right now. So you'll notice that a very quick registration code is required to use any of the Express products the first time in SOLIDWORKS 2015. Okay, so it's available in every package, but it is limited. We generally say to people, if you're doing real analysis, you're typically doing it on an assembly. Right? No one builds parts in isolation. They always have a job to do in with everything else. So what we consider the true kind of entry-level analysis tool, and these packages have changed very slightly, but we have a package called SOLIDWORKS Simulation Standard. Okay, and this does, the primary thing that this does is linear static stress analysis of assemblies. This is the bread and butter of stress analysis. It's probably 60 to 80% of all analysis that is performed today is linear static stress analysis. We assume a linear material model, so we're talking about metallic components or hard plastics below their yield strength, and we assume static loading, no dynamic effects, no vibration, no shock, those sort of things. Also in Simulation Standard, you get fatigue prediction based on those static load inputs. Right, so instead of understanding, whether it's going to fail on the first application of load, you can start to look at the predicted life of the part. You get a tool called Trend Tracker, which is like a virtual logbook for analysis. Keeps track of all the things you've tried in a model and lets you revert back to the best one or a previous one. And you get SOLIDWORKS Motion, kinematic motion analysis. Now, where this gets a little bit confusing is some of these things you also get as part of SOLIDWORKS Premium. SOLIDWORKS Premium is our top-level CAD package. Okay, and that includes the stress analysis and motion. Okay, so if you want to move into analysis, there's kind of two ways you can go. You can either buy the simulation standard package, or you can upgrade your CAD package. And there's pros and cons to both, and we're happy to flesh those out with you. Okay, but let's actually look at some real stuff here. Let's look at these processes. So let's start off with the linear static stress analysis of this little suspension bracket. All right, it's nice and simple, be quick to process. In a SOLIDWORKS assembly or a part file, we can set up as many analyses as we please. See, I've got a number stacked up at the bottom of the screen here. And I'm going to start a new one here, a new stress analysis, linear static stress analysis. As we start to talk about other types of analysis, we'll start to engage some of these other options. Now, the process for working in stress analysis in SOLIDWORKS is typically to start at the top of this analysis tree and work your way to the bottom. Right? There are 4 main areas that we will have to consider as kind of users guiding this analysis, and then there are 2 areas that we're going to have the software perform for us. Okay, so we start off with what these components are made from. I've got 3 independent components in this model, right? And each can be assigned a material definition. If I've defined a material in the SOLIDWORKS CAD model as I developed it, that'll automatically apply here, which can save me some time. But for now, I'm going to assign an aluminum to that bracket, right? Fairly extensive libraries of materials here. The key things we're interested in whatever unit system we find most comfortable, the elastic modulus, that's the stiffness of the component, and the yield strength. So we'll assign that. I'm going to pick a steel for the ball and also for the pin that goes through the middle. Got nice drag and drop functionality to apply materials to different things. And I get a little check mark saying all your materials have been defined. Also in this area is the place where I can choose to use shell or beam definition for components. Those shell is good for components that are thin, like sheet metal. Beam is good for things like structural members that have a constant cross-section. None of that applies here, so I'm going to mesh and analyze the true shape. Connections, there's 2 things in here. The first one, and most important, is how do these parts interact with each other? Okay, when part A, when the ball comes into contact with the bracket, are they fused together? Are they glued to, are they tied together, bonded, or are they free to slip and slide independently of each other? And we can either adjust this globally, adjust it for everything in the model, to say, hey, everything's not bonded. It's free to slip and slide and move relative to each other, which is what we call no penetration. I can do that globally, or I can do it locally. I can say, hey, at the interface between this component, I'd like to have a sliding relationship. So, and there's automatic tools for locating these areas. So find me all the interactions between these 2 parts, and it will highlight them for me at top and bottom of the ball. So a great mix of automatic and manual kind of tools, automatic application of everything, manual adjustment where we need it. The other thing that's involved in this connections folder is virtual connecting components. Bolts, springs, pins, to welds, to tie things together. For example, with a bolt, it's going to include preload from that bolt connection. It's really intelligent ways to allow you to remove the physical bolt from the model so you don't have to mesh and analyze it, and replace it with a virtual connection, which can do it more efficiently and sometimes even more accurately. Next thing to consider is how this object is held. Simplest thing to do would be to say it's rigidly fixed at these 3 support holes, but we can independently kind of control the how the restraint of different things, and this will have a big effect on the stress result you get. So, for example, start off at the 3 hole locations. I'm going to assume they're basically pinned, right? We call it a fixed hinge relationship. The diagram shows a little graphic of what that means. Basically saying, you know, the whole location does not change, but it's free to twist locally around it if loading causes that to happen. Okay, I might also consider the back of this is up against a large, broad, stiff object. So I'm going to prevent that from moving off plane. And we can actually independently control the degrees of freedom of faces or edges or vertices in the model, either based on a Cartesian, cylindrical, or spherical coordinate system. It's a really rich control there. When it comes to loading the model, this is often what I think the easiest piece of the puzzle. Right? It's just a case of applying whatever your design loads are at the appropriate positions in the model. But we can apply forces, torques, and pressures. We can apply the self-weight of the object due to gravity. Can it hold itself up, basically? Centrifugal loading if it's rotating. Temperature loads will cause thermal expansion and contraction. Can be interesting. Or we can force it to move. Hey, say, hey, I want to stretch this by 0.010 of an inch. Show me what force is required to do that. But in this case, I'm just going to pick a certain direction here. Apply a load of, 6,000 newtons. Again, whatever unit system you're comfortable with, it'll convert on the fly for you. Apply that into the model. And for this little simple sample here, I'm done. Materials, interactions between parts, I'm assuming they're all bonded for quick approximation. How it's held and how it's loaded. All right, 2 phases the software is going to do for me, or let me help with, is to mesh the model. Right, so for any finite element analysis, you're breaking the model down into a grid system. We use a tetrahedral grid, 10-node tetrahedral elements, and see that it'll map to that automatically. Now we do retain some control, and anyone that tells you that mesh is not important for stress analysis is lying. Right, the density of the mesh influences the quality and the accuracy of your result. We've got great automatic tools for automatically improving the mesh to a point that you can trust that result, but we also retain manual control. You can just pick a couple of faces here in the model where I'm expecting high stress values and tell the software to refine those in more detail. And that's a much better strategy than meshing the whole model at that density, so it'll take much longer to process. And then the final phase is to actually run the process, run the analysis. It's a 1.5 second solve on my system, which is just kind of regular old, it's an engineering laptop. 8 gigabytes of RAM, quad-core processor at 2.4 gigahertz, so good solid computer, but no rocket ship. And we get a prediction of the stress levels, of how far it's moved. We can animate those predictions, exaggerated about 75 times right now, so you're not really going to see that motion. And we can take a prediction of the factor of safety, basically a prediction of how close to yield we are. And it's predicting right now in some of these regions that I'm beyond yield. So I would need to look at a stronger material than the aluminum alloy I picked, or a much thicker design in order to have something that was safe here. And feel free to log a question if there's anything that doesn't make sense or anything you want me to kind of double down on, or if it's something you're curious about. But moving on from here, we've got kind of a stress level, 128 megapascals. And let's just change that unit to something that's easier to read off. Okay, 128 megapascals. The best thing about having this in SOLIDWORKS is if I want to explore something else, right? Let's say I change the material to something stronger, and I want to come in and manipulate a certain dimension. Maybe it's this one here. Let's see what happens if we make that thinner. From 5 to 4.5, rebuild the model, you see the change reflected on the screen. As soon as I do that, the analysis is ready to be reprocessed with the new geometry. It will remesh based on my previous settings. And, in a cycle time of 15 seconds or so, we now have a prediction of how that stress might change based on the design change. Right. So having these things integrated into your CAD system is a huge advantage. Now, once you've got your stress analysis result, slightly different model here. Once you get stress analysis result, one quick thing that you might want to do is to see how this is going to react upon multiple loading. This suspension bracket is part of the steering system. This load that I've mimicked here is an analog for the action of turning the steering wheel. That's not going to happen once in this product's lifetime. It's going to happen thousands upon millions of times. So it makes a lot of sense after you've done a static stress analysis, and this is enabled by Simulation Standard, to take that loading and to say, basically, what if I run the same loading in a fully reversed fashion? So I'm going to apply it from the left, and I'm going to apply it from the right. Go ahead and do it 1,000,000 times. And we can run a fatigue analysis here. And this fatigue analysis is based on an SN curve for the materials. You can either read them in, you can use an approximation. There's a couple built into the software. All right, but this SN curve defines how that object will react to fatigue. So SN is stress versus the number of cycles to failure. And once we've run that, we get a prediction, effectively, of design life. How many cycles can we get through before we'd expect to see some sort of fatigue failure? And in this case, I'm at about 2.6 million. So we're going to go back and compare that against expectation. So Simulation Standard, those are the types of things that you can address in the Simulation Standard tool set. And some of those tools are also available in SOLIDWORKS Premium. The step up from there, the next kind of step in the tour, is a suite of tools called SOLIDWORKS Simulation Professional. And this adds kind of a number of other modes of failure or other types of assessment you can do to the essential stress analysis tools. For example, it includes everything that's in Simulation Standard. Allows you to make predictions of failure due to buckling, right? Instead of overstress being the failure, instability or buckling behavior could be the failure. It introduces the ability to look at the resonant frequencies or to do a modal analysis. Okay, if you've got anything that's in a vibratory environment, that's going to be important. We have a technique called submodeling, which lets you basically model a large system, maybe with coarse mesh and simplified assumptions, because large systems can take time. And it allows you to run a second analysis after that drills in and focuses in on a particular region of the model. And it also introduces an optimization tool. So let's start off by looking at that. So you remember if I ran the stress analysis and I was double-clicking areas of the model and making adjustments to certain sizes and running the analysis again. Great way to explore a model, but what if we could automate that? And that's what optimization allows us to do. Basically allows us to identify particular dimensions in the model, in this case the radius of these scallops, the thickness of that flange I was playing with, and tell the software to go ahead and vary them. I've also asked the software to consider a stress limit. Hey, I don't want my stress to exceed 150 megapascals. That's less than the yield strength of the material, but I'm building in some factor of safety there as well. And we go ahead and hit run on this, and what it will do is automatically adjust the model on the screen and run stress analysis on each adjustment. If you watch closely in the main view of the model here, you'll see the model changing. You also maybe hear it dinging there. It's just indicating each step is finished. As it's doing that, it's racking up stress results for all these variations. Okay, one here just exceeded the limit, and so it is colored in red. Right, but it's doing this design exploration without me having to touch anything, just basically watching and observing at this point. When it's finished, just got 2 steps to go. When it's finished, we can revisit every single one of these iteration steps. We can pick it and then maybe modify the model from there. It's very simple for us to just click on some of these items, see what's going on. We can also interrogate the stress results for that case. As we click through, you'll see it adjusted. We retain some design exploration type tools. I can manually adjust that radius on the screen to see what's happening. And so this optimization is a fantastic way for us to explore different design alternatives, different things we might want to explore live on our screens without having to manually create every step. Now, in terms of, we start to talk about dynamic loading, shocks and vibrations and things like that, that we're doing more and more qualification on. The first step towards dynamic loading is to look at the natural frequencies of the structure, and that's also enabled by SOLIDWORKS Simulation Professional. And if we're looking at the natural frequencies of the structure, we're running a frequency analysis. It's also called a modal analysis. Basically what that's doing is looking at the materials that are built into the object's made of, looking at where it's restrained, and identifying the frequencies, the vibratory frequencies that will cause resonance. Now typically, for most applications, resonance is bad. If you've got a motor mounted to a frame, and that frame has a natural resonant frequency that's the same as the operating speed of the motor, you're going to have a very shaky frame. It might be noisy, it might be annoying, or it might be a pile of metal on the floor by the time you're done. But frequency analysis helps you identify, basically I've got one here that I've solved, the resonant frequencies of that structure. Okay, we can view it graphically here. We can also view it numerically. Sorry, we could view it in a table there. We can also view it graphically, shown here. But this is telling me that if I put this object into a vibratory environment at 2300 hertz, 3400 hertz, 7,500 hertz, whatever it is, I'd expect to see some sort of vibration problem. And often that's enough information to design around. If I'm putting this on a vehicle, so we can probably assume it's going to see vibrations you know, in the 0 to 1,000 hertz range. That might even be pushing it. If my lowest natural frequency is 2300, I'm likely not going to experience any vibratory problems. So, but we get no information there of kind of how bad, how much it's going to move, how much it's going to vibrate. All we get is kind of a general shape here of the direction we'd expect it to move. So if I was to excite it at 2300 hertz, I'd expect to see it waggle up and down like this. And again, that can be good design information. If that's a problem, I stiffen these connections to make it harder for it to move in that aspect. But to really get any real information about the response of an object to a dynamic load, or if you're trying to replicate testing that you do in the real world on a shaker table or a shock test rig, you're looking at a top-level stress analysis package, SOLIDWORKS Simulation Premium. Okay, and there's two major areas that Simulation Premium opens up for you. One is dynamic loading, and the other is nonlinear effects. The third one is composite material analysis, analyzing the strength of a laminate or a layup of different layers of composite material, with typically a fiber composite material with fibers running in different directions. Okay. But from a dynamic perspective, there are three, actually there's more than three now, three main types of dynamic analysis. And what they really vary is how we apply the load. We have time history analysis, which basically is saying, I'm going to supply some sort of input that changes with time. It might be a shock or it might be an impact. Harmonic is pure vibration. I'm going to subject it to vibration of different frequencies. And random vibration is based on an input called a PSD input, power spectrum density. It's a good way to characterize a complex vibration signal, like what you experience on an airplane or a ship or in a vehicle traveling down the road. So how that relates to the software, right? My frequency analysis tells me which way this is going to move, but you'll notice there's no force for starters, there's no value to the input, and there's no value to the output. Dynamic analysis changes that a little bit in that I express some sort of dynamic input signal. In this case, I have a 50G acceleration that's being applied to the supports. So basically I'm saying whatever this is mounted to is moving, it's accelerating at up to 50G. The time history of that input is a very sharp, sudden spike, a shock, if you will. Right. This is what we call a classical shock pulse. It's fairly standard approach. It's 11 milliseconds to go from 0 to 50G, and then it's fairly quickly removed as well. And we let the analysis run a little bit afterwards to see what happens. So we've now got a dynamic load and dynamic input. When we solve that, because we're talking about dynamics, we don't just have a stress picture, we almost have a stress video that we can look at. Now this object's pretty stiff, so what you see is, the input kind of move with the shock, and if you look closely, you'll see it kind of vibrating afterwards as those vibrations damp out. So this is an example of a time history where we're actually getting real stress values, real stress peaks based on this dynamic load, this dynamic action that's occurring. Now we can also pull out a variety of different, information. We call it looking at the response of the system. This is basically the displacement versus time curve of a point in the model that I just picked randomly. So a large initial shock, see the peak value there, how much it's going to move at its peak, down to some kind of low-level vibration that dies out. And so we can look at that both in the time domain, like I've just done, and also in frequency domain, which is typically how we look at vibration. Now, the other main area of the simulation premium package is nonlinear analysis. And nonlinear analysis comes into play in two main areas. I get a little, this is basically the clip off the side of a pen, right? And if you go ahead and run a stress analysis on this with a load at the end and fixed at the other end, you get a message that you may or may not have seen if you've done any analysis saying that we've got large displacements. Okay, basically that it's moving a lot. Now, linear static stress analysis, the bread and butter of analysis we talked about, assumes that loading causes small deformations. Basically, that the shape of the loaded part is not significantly different from the shape of the unloaded part. As soon as we start violating that assumption, we move into what we call a nonlinear analysis. And our software, Simulation Premium, will assess that shape change by solving the analysis incrementally. I'm running analysis here. You'll see it kind of moving on the screen there. Now, this is a brand new feature of SOLIDWORKS 2015 is that when you run a nonlinear analysis, it will animate the result as it's solving, which is pretty cool. You can actually see what's happening as the solution is progressing. But this will give us a much more accurate prediction of how that shape changes under load, how the stiffness of the geometry changes under load, and how we get an accurate prediction of the finished part. The other thing that's happening with this model is that the stress is exceeding the yield strength, which means we have permanent deformation that will occur. Now, to account for that, we also need to go look at our material models, because a linear static stress analysis cannot account for that permanent deformation. Nonlinear analysis allows us to enable plasticity models of different types, or hyperelastic for rubbers and silicones and things like that. Basically, I can say that once I exceed the yield strength, I want you to switch to using the stress strain curve of the material. So we're actually going to see the permanent deformation. We're going to be able to analyze exactly what happens. And this, with large displacement and nonlinear materials, is the one that most closely approximates, well, it will be the real life behavior. And so nonlinear really allows us to break down those two doors: large deformation and post-yield or hyperelastic materials. And if you have a situation that involves either of those, you really need nonlinear analysis for an accurate prediction. And we can even do things like look at loading and unloading phases in the model, see what sort of permanent deformation you might have. Right, so I've got a scenario here where I'm basically applying 3 sets of loading. Each one deforms it a little bit more until we get to a final phase. Just to show you, here's the loading history that this is based on. Slightly increasing load each time. Yeah, so nonlinear analysis is becoming more and more prevalent. It's becoming easier and easier to do. So it allows us to analyze those materials and large deformations. So that's kind of the tour, right? Starting with kind of linear static stress analysis, moving into other modes of failure and other kind of analysis productivity tools as you move up into the simulation professional realm, and getting into nonlinear and dynamic analysis at the top end. Now, I did want to highlight a couple of things that are new for 2015. We are having a full webinar on some of the new features in 2015. We find a lot of our customers wait until the new year or later to upgrade, and that's certainly good practice. So it's a good time of year to modify. So we get a lot of questions about new material this time of year. Two things I want to show you that are new in SOLIDWORKS 2015 with regard to stress analysis. First one here is a tool called the Load Case Manager. And what we find is that a lot of the time, you have a certain set of analysis loads, maybe a downward load, a side load, maybe a torque, and you need to apply them in different combinations, different scenarios to satisfy the full, range of things that can be seen by the product. And to do that right now, we'd need to set up independent studies that define each load case. But what if I could set up one study and review all my different loading and support conditions in a table? So instead of setting up whole new studies, I'm just putting new rows into a table to identify these different loading cases. Whether it's a downward load, only has the downward loading on. Lateral load, only the sideways loading. Torque values, right? And then we can go in and combine things, right? I can say, hey, downward plus lateral. Mathematically figure that out. You don't need to run a new analysis. Just figure out what that combined stress will be. So the top area here is actually running the analyses. The second area is just combining them mathematically. But the cool thing about it is you get full interrogatable results for every single one of them. So we click through here. There's my torque results. Show twisting. There's a lateral load. There's a load pushing it upwards. And you get it presented to you in a tabular format, so you can just read off peak stresses, or you can go interrogate the complete model. So really clean, fast way to work, and that's called the Load Case Manager. It's part of Simulation Professional. The other thing that's pretty cool is I showed you before on the steering bracket how you can get a fatigue life prediction based on a static loading. But often we want to understand how fatigue occurs based on dynamic inputs. And if anyone's got a test spec that says something like, run the object on a shaker table at a certain frequency for 3 hours and see if anything breaks. Right? With dynamic fatigue. Now we can approximate that in SOLIDWORKS 2015. We can use a dynamic analysis like I have here. Right? This is a vibration analysis, so it's basically showing me how much stress is developed if I was to run it at 440 hertz-ish. I can tell the software to go run a fatigue approximation based on that stress level from the dynamic study, and then I've scaled it 3 times just to get an interesting result. But then I can get a prediction of the number of cycles I can get through at that frequency before I'll see failure. Can also incorporate results from a random vibration study. So that's all pretty interesting stuff to explore. So again, new in SOLIDWORKS 2015, the likelihood of failure due to dynamic loading effects. And actually it's just due to things like vibration. Edit that. Okay. So that's an overview of the stress analysis tools. 45 minutes to an hour is nowhere near enough time to explore all the things that it can do. And as we go through the year and schedule more of these, we'll dig into certain phases of these tools in much more detail. However, we do have a really useful document. It's called the Hot Career Simulation Buyer's Guide. You'll find it on our website. And it's a really in-depth discussion in plain, kind of non-analyst language of what the different packages do. And I'll say, look, if you have a dynamic scenario, here's what you're going to get out of Simulation Standard. Here's what you're going to get out of Simulation Professional. And here's what you're going to get out of Simulation Premium. So you can intelligently select the tool that's best for your application based on the types of material you need. So I'd encourage you to go ahead and download that. Pretty interesting stuff. The other thing that's important to realize is that there are a variety of ways that we can help you. Okay, so when you're sitting down to an analysis project, let's say you're new to analysis and you're doing it for the first time, we have a range of offerings. Right? We put a bunch of stuff on YouTube and our blog, and you can go to the SOLIDWORKS discussion forum and you can look at other resources on YouTube. Right? And you'll find all these self-help resources, videos that people make. They're available to everyone. They cost you nothing. Good tool to keep your tools, to keep your skills sharp, but it's effectively self-help. Right? If you don't know where to get started, sometimes those videos cannot explain things in the depth you're looking for. That's completely free. Our subscription service customers have access to technical support. Okay, and technical support, we have degreed engineers on staff manning our simulation technical support line. Right, and we're here to answer your questions. Right? Hey, I see this on the screen. I'm not sure what it means. What is it? Hey, I'm trying to apply this restraint and it won't let me click where I want to. How do I get that in place? Hey, I'm not getting the results I expect. Based on how I've set it up. Can we chat about those sort of things? And so that's available to our subscription service customers. But then we also offer training, and training is going to offer you guidance on the best practice techniques and processes to run software effectively. It's more holistic than technical support. Instead of you asking the question, it's telling you what the questions should be and what your processes should be and giving you that structure to run analysis. So we offer training both online and in classroom at locations right across North America. But a step up from training, which is based on kind of standard training models that we've put together to convey the concepts as quickly as possible, we also offer mentoring. And mentoring is kind of the ultimate training experience. It's dedicated one-on-one assistance, or one of us with a couple of your team, based around your models, your challenges, your design information, and we'll teach you how to plan, execute, and review those analysis processes. Okay, so as you move kind of down this cascade here, you get more customization and more relevance to what you do, but it's a little more involved as a service. And also put consulting on here. It's the ultimate customization that it's typically completely hands-off. Right? You say, here's a project they need completed. Again, we'll give you an estimate of time and cost and go off and do it for you. Present you with the results and deliverables. So all those offerings are available. A little more information here on kind of mentoring and consulting. But the services we offer, we don't do a good job of talking about them. So if you're interested in anything here, please feel free to give us a call. Either your account manager or put a note in your survey. So general contact information is on the screen. Happy to address any questions you might have about anything you saw today or anything we do around stress analysis. If you want to ask them now, good time to just put them into the GoToWebinar question panel. But you'll also see a survey as you leave. It's an opportunity for you to ask questions or pass comment on what you've seen today. Encourage you to do that if there's anything you want to convey or discuss. But otherwise, as we kind of go through January here with this new kind of webinar format we're working on, you'll see a SOLIDWORKS webinar this afternoon. Revisit simulation next week with some kind of deeper education on what's new in 2015 simulation. And then PDM, CAM, and SOLIDWORKS events for the rest of the month. So that takes us a little over the 45 minutes I promised you. I hope you found it informative. I'll be here. I'm ready to answer any questions you might have, so please don't hesitate. So you're curious about something or you want clarification on something, just put a note in that question panel in GoToWebinar, and we'll be happy to address it. But otherwise, I thank you very much for your time, for joining us this morning here on the West Coast, and in the afternoon if you're elsewhere. And we hope to see you at another event like this in the near future. So thanks again, and I'll sit here for a few minutes and see if there are any questions that people have.